Okay, so now what we're going to do is talk about another theorem, which is Descartes' rule of signs. And again, this theorem is not going to really tell us much about finding the zeros, but it is something that's very helpful once we have kind of, found all the zeros, or to kind of know what we're getting ourselves into when we're trying to find the zeros of a polynomial. And basically what I'd like to do is kind of, explain it to you first, and then kind of talk about, look at some problems and kind of identify, how it can be helpful. So basically what Descartes' rule of signs, is kind of two things that it's going to tell us. It's going to tell us the number of real positive zeros as well as the number of real negative zeros. And then from there, we can determine how many complex zeros a polynomial has. And I kind of have a nice little way that I kind of work that out. And now again, it's only telling you what the possible combination. It's not telling you this is going to have exactly, this many zeros unless it's, unless it comes to a one number or not, which we'll get into. But it's usually giving you multiple numbers for the possible number of zeros. I know that kind of sounds confusing. So what we're looking at is to identify the number of real positive zeros. You're basically looking at the number of sign changes. When does, between each term, how many times does it go from positive to negative or negative to positive? So for example, if it goes, let's say there's 4 sign changes, okay? So if there's 4 sign changes, I'm actually going to show you how this kind of works. So let's say you have 4 sign changes. It goes from positive, negative, negative, positive. So that means you could have a possibility of 4 real positive real zeros. But then it says subtract an even number. Now usually the easiest one to work on is 2. So you could subtract 2. So let's do the possible positive real zeros. So if you have 4 sign changes, okay, so you could have 4, or you could subtract 2, which is an even number, so you could have only 2 positive real zeros, or you could subtract 2 again, or like 4, and you'd have 0 positive real zeros, okay? So therefore, that is the possibility of your basically your real zero. So you could have all 4 of them would be positive real zeros. You could only have 2 positive real zeros, or you could have none at all. Now, then the next thing is you can evaluate for f of negative x. And when you evaluate for f of negative x, let's say the negative real zero, let's say you have 3 sign changes, okay? So if you have 3 sign changes, again, it's minus an even number. Well, the only even number you can subtract from 3 is going to be 2. So 3 minus 2 is 1. So what this tells you is that there has to exist at least one real negative number, all right? There has to exist at least some real negative number. Now, in this case here, you can see that if we have, positive and negative, it is possible here to have 3 negative zeros or 3 real positive negative zeros and 7 there. So I didn't really kind of go through this, but let's, your equation is going to be like x to the 7th is the degree. So by the fundamental theorem of algebra, we know that there's going to be 7 zeros. So all 4 of them could be positive real, and then you could have 3 negative real. All right. So then what we can do is we can kind of deduce to be able to determine the number of imaginary zeros or complex zeros. Well, if there's only 7 max, right, then if they're 4 are positive and 3 are negative, and they're both real, then that means I have a possibility of 0. And I'm just going to use I for the complex. Let's just use C, actually. So C represents the complex. However, if I have to have 7 zeros, right, fundamental theorem of algebra tells I have to have 7 zeros. If 2 of them are positive, right, so I guess we could go from there. So you could have 2 of them are positive. You could have 3 of them are negative. That means you're going to have 2 that are complex. You could have 4 of them are positive, or you could have 4 positive and 1 negative, but again, that'd still be 2. You could have 2 of them are positive, 1 of them is negative, therefore you could have 4 that are complex. But then what you notice is you could have 0 and 1, and therefore you could have 6. So what this is basically showing us is the possible, so you could have 0 positive, 1 negative, and therefore you'd have to have 6 complex zeros. So what this is doing by using this is telling us here is the possible arrangement of positive zeros, here's the possible arrangement of negative zeros, and here's your possible opportunity of complex. Now, that probably makes a little, whenever I'm explaining this, it's kind of like, okay, well, how can I use this? So let's go and look at some examples here and to make sense of it. All right. Now, the first thing we want to do is just count the number of sign changes. So you can see here, no sign change, positive, positive, no sign change, positive, positive, no sign change, positive, positive. Okay, great. So the number of real positive zeros So the number of real positive zeros is equal to 0. Now let's look at the real negative. So to identify the real negative, you just evaluate for f of negative x. So now I'm going to plug in a negative x in for x. So I have 2 times negative x cubed plus 2 times negative x squared plus 5 times negative x plus 4. Okay? Now, remember, any negative number raised to an odd power is going to be negative, and any negative number raised to an even power is going to be positive. So here, I'm going to have negative 2x cubed. Here I have plus 2x squared. Here, I'm going to have a negative 5x, and then plus 4. And then again, as you count the number of sign changes here, you can see there's 3 sign changes. Minus an even number, you're going to have 3. So I'm just going to do it this way. So the number of positive is equal to 0. The number of negative could be 3, or it could be 1. So therefore, the number of complex, now again, look at your degree. Your degree has to be 3, right? So if you have 0 positive and 3 negative, then you're going to have 0 complex. But if you have 0 positive and 1 negative, that means you have to have 2 complex. So therefore, that would be your opportunity when you go ahead and solve this. Like, for instance, if you have 4 complex, or 1 complex 0 or whatever else, you just realize there's going to be a mistake. Or if you go ahead and solve this and you're trying to factor it, you know that none of the zeros are going to be positive, right? So, I mean, it's really just kind of one of those that helps us better understand the problem. And again, we'll kind of work our way backwards up to some of these problems looking at that to really kind of identify it. All right, but in this next example, and again, one other thing, you want to make sure that your polynomial is in standard form, which I didn't talk about it, but I noticed they were both in standard form. So the number of zeros here, sign changes, is going to be 1, 2, 3. So the real positive is going to be 3, and then minus 2 is going to be 1. Now let's look at f of negative x. I don't know why I did that. Whatever. F of negative x is going to be 4 times negative x to the 4th minus negative x cubed plus 6 times negative x minus negative x minus 6. Whew, that's a lot going on there. That should be squared minus x. Okay, so let's see what we got here. That becomes a positive, so it's 4x squared. That becomes a negative times a negative is a positive. That becomes a positive, so that's 6x squared. That becomes a positive minus 6. So the sign changes? No, that's not a sign change. Looks like there's only one sign change here. So I have positive equals 3, 1. Negative is equal to 1. And therefore, for complex, again, what is my power here? It's going to be 4. So if I have 3 positive, 1 negative, that means I have to have 0 complex. But if I have 1 positive, 1 negative, that means I have to have 2 complex, okay? So let's go and take a look at this and kind of see how this might be, useful on some of the problems that we kind of already solved. So for instance, when I look at this, I see that there's no sign changes. That means I'm going to have no real positive zeros. And if you look at my zeros, I didn't have any 0 real positive zeros. Over here, you look at here, you see there's one change, 2 changes, 3 changes. So therefore, I could either have 3 real positive zeros or 2 real positive zeros. I'm sorry, 3 or 1 real positive. And you can see I only have 1 real positive zero. 1 is positive, 1 is negative. That means the other 2 are going to have to be complex. For instance, let's look back up here. This one over here, you can see that there is, 1 sign change. So therefore I know there's going to be 1 real positive 0, which was already given to me. And there it is. Okay. So it's really kind of one of those that, or this one has, yeah, this one's a negative and positive. So it's really one of those theorems that, helps us kind of further understand. But with the use of technology, it's not something that, has been needed, but needed for us to really solve the zeros of the polynomials, but I think it is really helpful, and it does come up quite a bit, especially the question is identifying the complex zeros. So if you can identify the number of sign changes to find the positive, just make sure you subtract an even number to get all the possibilities, then evaluate for f of negative x, and then find those sign changes and subtract. And then just remember that the number of positive plus the number of negative plus the number of complex always has to add up to your degree of your polynomial because of the fundamental theorem of algebra. And a lot of the questions that I see is basically just asking you like how many complex zeros. So it's making you do this math to get to the number of complex that you can go ahead and answer. But that's really kind of basically it with the Descartes rule of signs. Now we'll just kind of get into writing the equation of the polynomial to wrap everything up.